distance from the star formation main sequence, the RSB parameter in the Elbaz et al. Parlance, color-coded by the mass-weighted stellar age of galaxies that we have determined with SCD fitting, in which the star formation history is also a parameter of the fit, is not kept constant. And the two plots are for low-mass galaxies, where low mass means less than 3×10 to the 10 solar mass is stellar mass, obviously. And high mass means bigger than that, from the candle's good south and good north fields. And is divided in 4 redshift bins as labeled. So what you notice, let's focus first on the high mass galaxies first, is that so the main sequence here is, main sequence galaxies are those between these dashed vertical blue lines and the green lines. Above the blue lines are what we call starburst galaxies. Below the green lines are green valley or sub-main sequence or quenching, choose your nomenclature, galaxies. And below these yellow lines are galaxies that are quenched. Their specific star formation rates is of the order of less than a 10th. I think we fixed less than a 10th or a 30th, I forgot, of the Milky Way. That's our definition of quenched, okay? So the first thing to notice is that galaxies are on the main sequence spread the full value of core density. Sigma 1 is the average stellar density circularized within a radius of 1 kiloparsec. Okay? Whereas galaxies that are about to quench or already quenched distribute in a narrow value, which is about 1/3 in log space of the full range, and which seems to top for massive galaxies just shy of 10 to the 11 in log space. Low mass galaxies exhibit a wider spread. They occupy the full spread of density when they form galaxies, stars. But once they quench, they also do qualitatively the same behavior, but their excursion is wider than high mass galaxies. This is an identical study that has been done by Guillermo Barro here, Santa Cruz. The paper came out in 2015. This plot is actually from the 2015 paper. The 2017 paper is the one that is now on the APJ. The plot here is tilted. So now density, let's focus on this one. Density is here. There's a slight difference in that Guillermo doesn't use the absolute value of sigma 1 that I have used, but he uses the differential value relative to some fixed value. Given the narrow range, especially for quenched galaxies, the two are quite similar. But this definition of the central density gives you the opportunity of actually stacking everything together, regardless of possible variations of sigma 1 with the stellar mass. Plotted here is the specific is delta star formation rate, which is essentially identical to the RSB parameter. As you can see, they find the same thing: very narrow excursion in density for quenched galaxies. Now, so we have 3 variables here. We have age, we have, as we have measured, we have stellar mass, and we have sigma 1. One would imagine that age would be the independent variable, but the measures are noisy. And in fact, a much stronger correlation is the one shown between stellar mass and sigma 1, reproduced here. And other people, this is from Bomili's paper, which is being referred these days. But you can find similar correlations in the literature as cited here. However, we measure the stellar age, and you can certainly see very nicely that for a given stellar mass, older galaxies are definitely have a higher stellar density, suggesting of some sort of transformation, at least inside the innermost 1 kiloparsec radius. But this strong correlation tells us something even more important, that more massive galaxies have certainly a stronger sigma 1. And if you think sigma 1 as the result of some dissipative gas accretion, some dissipative product, it tells us that more massive galaxies must be more dissipative. When galaxies are quenched, now these differences between star-forming galaxies and quenched galaxies, this is a UVJ diagram difference. Qualitatively, they exhibit the same thing. I'm not going to talk about the different slopes in these two regimes that has been talked about by others. I'm going to simply focus on the dependence of with the age. Now, you can see the dependence of age. In fact, if you plot now stellar mass versus age, and you color code the points, the galaxies, with sigma 1. When galaxies evolve, when they form stars in the main sequence or in the starburst sequence, in fact, you do see the stellar mass grows as they age, but certainly the densest galaxies occupy the upper right point, the part of the plots where they are more massive and older. As galaxies quench or start quenching, this trend of increasing stellar mass with age disappears, mostly because the age differences become compressed relative to the stellar age, and the plot becomes vertical. But and so you cannot see the trend with higher sigma 1 anymore, but certainly more massive galaxies are the densest one, as we know from the correlation. You see the same here. If you choose to plot this time sigma 1 versus age, and you color code by stellar mass, so the most massive galaxies are the oldest, and the densest ones. And again, the plots show the correlation with age when they evolve, and becomes progressively more vertical as they quench. Now, let's think about what sigma 1 teaches us about. Sigma 1 teaches us about, is a local metric of density, right? It informs us on the structure of the innermost volume of the galaxy, to the extent that we can measure it reliably. But we think we can measure it reliably. It doesn't really tell us much about how and if a galaxy transforms itself on broader scales than the core, on larger scales. Okay, I call it global for lack of a better name. It just tells us if the galaxies grow a high-density central structure. Which other metrics can we think to try to monitor the more global value? Well, galaxies, as they evolve, they grow in size and mass, right? And so you have to factor in that they would change their size and their mass anyway, even if they grow self-similarly, even if they don't transform. So I thought I want something that does not depend on the light profile, on how the light or the mass is distributed. And because I don't have much fantasies, I simply borrowed what others have done, Gini and M20 in particular, as global metrics. They're nice to me because they describe the overall light, and to the extent that light traces mass distribution, thanks Richard, independently on the light profile. Also, I'm going to use them in a totally different way relative to how they are used traditionally, namely as classifiers or morphology. Not at all. Their absolute values are difficult to calibrate. I'm not classifying morphology here. I'm using these two parameters as a global, as an inequality metrics. They tell us how galaxies distribute their wealth, their stellar mass, in their volume elements. You can think of a three-dimensional Gini coefficient. It's not that difficult actually to even build it. So what we're going to do, we're going to measure variations of Gini and M20 as information content. And then we're going to talk about new definitions of compact galaxies, although this is not really what the point is. All right, so what happens to this? Well, first, if you look at sigma 1 again, let's go back to sigma 1, and you study at its distribution with redshift, what you see here is colored histograms. Our lowest redshift being 1.5 to 1.2 to 1.5 is in black, 1.5 to 2 is in blue, 2 to 2.8 is in red, and in green there is the highest spin, lowest statistics. Formally goes to 4, but again, there are like 3 galaxies at 4. And then now we have 3 mass bins, 6 10 to the 9, 6 10 to the 9, and 3 10 to the 10, bigger than 3 10 to the 10. Sigma 1 doesn't really change much. The upper value does change with stellar mass. We knew that, strong correlation. But within the redshift bin, the highest value stays where it is at the end, right? So galaxies, we have seen that when they become passive, they tend to pile up in the highest bin of the density distributions, and this plot will shows all galaxies together, regardless of their star formation history. But we'll see when we slice it, does the same. So essentially, the highest value of sigma 1 is where the evolution ends. This is now the cumulative distribution function of sigma 1, this time sliced between star-forming and quiescent. Again, my previous statement of very little evolution stands. There is a little bit of a hint of evolution in the low mass bin between, the very high redshift bin and the lowest one. But overall, there is a much evolution. Situation is very different if you look at Gini and M20. This is the evolution. Oops. This is the evolution of Gini. These are very large variations of Gini as galaxies evolve. Okay, and this is M20. The difference between Gini and M20 is that Gini informs us how galaxies distribute their light and hence mass in their volume elements. M20 informs us how nucleated they are. It doesn't say that there is only one nucleus. There could be more than one. So we have to go and analyze how often it happens that, two nuclei carries most of the light. It doesn't happen very often. But basically, this is an index of nucleation. This is an index of compactness. In both cases, the trend is the same. As galaxies evolve, going from high redshift to low redshift, they become much more compact and more nucleated. This is the same through the cumulative histogram. What you notice here is that the evolution happens both during the star-forming phase, but also during the quiescent phase. It is the strongest at high mass and during the star formation phase. The weakest for low mass. But you certainly see it also in the quiescent galaxy. And you can run your statistics to measure how significant this evolution is. And I tell you, it's quite significant. Now, this is the same for M20, okay? Now we can look at the same diagram we have seen for sigma 1, this time for Gini, color coding for age. It's not that dissimilar. This is the high mass bin, right? It's not that dissimilar, but you do see the evolution of Gini quite well. You see that Gini gets piled up towards higher value, which means more compact as the time clicks, as the time evolves, right? So you don't see, so this is the big difference. The distribution of sigma is invariant with redshift. It's always the same. So it means something is fast, it's going fast. This keeps moving in monotonically with redshift, right? And all galaxies become more and more compact, all of them, regardless of their star formation history. So I interpret it as evidence of a secular variation. Hence the title of my talk. This is the same for M20. Excuse me, this is the same for low mass bin. For the low mass bin, in full analogy with sigma 1, you do see that the excursion in value of Gini of the low mass galaxies is broader than for the high mass. Okay? To me, it looks as if the evolution has been interrupted for the low mass galaxies before they could complete their excursion. And you can see that, in fact, the variations of Gini is much less pronounced with redshift. We knew that the evolution from the cumulative distribution was less pronounced. This is the same for M20. Qualitatively, now, of course, M20 becomes more negative as galaxies become more nucleated, and you do see, right, the plot is tilted. Same story for low mass galaxies. So what are we seeing here? We're seeing the rest frame light at 4,000 angstrom or more or bigger. The lower the redshift, the redder the light. And this is the bulk of the stellar mass, to the extent our SCD fitting allows us to measure the stellar mass. This is the non-dissipative baryon component, the stars. Let me remind you that to a great extent, not exactly, but to a great extent, dark matter should behave, should respond to gravitational potential variations like the stars. So if this is not too wrong, this gives us the opportunity to study to see how the non-dissipative components of galaxies change. As they grow in size and mass, galaxies constantly become, seems, more concentrated and nucleated. They rearrange their mass by placing it in fewer and fewer volume elements. For lack of a better name, I called it global compactification. Incidentally, I read this interesting paper by Jonathan, Nab, and Nostryker, where they do consider something similar. And just to give you some numbers, okay, in going from 2 to 1, take a 10 to the 12 solar masses halo, this would release something like 5 × 10⁵ of energy. Calculate how many seconds are in this interval, and that gives you the luminosity. Half of it goes into heat because of the virial theorem. So my question, and their question as well, Jonathan was the first to propose it, does this help at least, or even totally quench star formation? It's a lot of heat. Okay? What is important, I think, is that this compactification, if it is real, appears to take place both before and after quenching, in particular after quenching. So although it might be started by the dissipative accretion of gas, it seems to continue when the dissipative accretion of gas has stopped. So it's not driven in the passive phase by gas accretion. So it looks as if there are two time scales here that regulate variations of the potential. One is fast, dissipation, is this gas, right? And it ends at quenching. And the other is slower, secular. That's why I use this word. And I don't know what is driven by. This is the non-dissipative component. I don't know how the dark matter, I mean, I know of dynamical friction, but I don't know much else. So I noticed that the dependence of Gini and M20, thank you, Richard, is similar to the one of sigma 1, but not identical. At any epoch, I stress, the distribution of sigma 1 is the same. That of Gini and M20 changes continuously. This is what suggests a secular transformation. By the way, having these three variables made me think of redefining what a compact galaxy is. Compact galaxy could very well be defined as something that has Gini bigger than something, and this something I define it to be bigger than 0.55 based on where the points distribute, with M20 less than minus 0.16, and this is the traditional Barrett-Hall definition of compact core galaxies. All right. I'm going to skip this because Richard is going to kill me otherwise, and just put my, no, it was fast. Conclusion. So galaxies change their structure as they evolve, even in absence of merging, obviously. They grow in size and become more compact and nucleated. And both star-forming and quiescent galaxies do this, okay, regardless of the density of the central region. And this continues after quenching. Perhaps it started by accretion of gas, but it continues afterwards. And since it continues, it poses the questions of whether or not the compression of the gas and heating up during the release of gravitational heating can help or cause quenching. More massive galaxies do dissipate much better than lower mass galaxies. And we don't really need a causal link between high density core and quenching. It looks as if that when the core density reaches its maximum value at high mass around log sigma 1 of 10 to the 11, the galaxy is quenched. The two things occur together, okay? And I haven't had the opportunity to discuss this point. We'll talk maybe later. All right, thank you.
But a puzzling conclusion that it leaves me wanting more, namely, do you have a physical mechanism in mind for why galaxies? Does it have anything to do with
quantum? So the plots support the overall secular evolution, right? And show that the quenching always happens when in the direction of happening when the secular evolution has compactified the galaxies, right? The detailed physical mechanisms, no, I wish I had one, other than the considerations that if this is really evidence of the readjustment of the overall gravitational potential of the galaxy, the virial theorem is pretty general. You do know that if there is gas in there, the virial theorem tells you this gas is going to heat up. That is the physical link to the quenching. That we know is very general, very. In fact, you can even write the equation of what is the variations of G in terms of the increase of the temperature increase through video.
Very deliberate that you just use the word AGN.
Very deliberate. I don't even know what the AGN does here. Although, let me notice, yes, absolutely. That I make no statement. I don't know what the AGN does.
Andreas, your question,
But my question quickly answer my I know this one. But I mean, I just have a short question about the scarcity. You take galaxies in the n of 1, and you assume the angular momentum is conserved. To make it a galaxy of n equals 4, it is complex. So nothing has changed. Only the profile is.
Absolutely.
So when we complex, I think we need a different path, not necessarily falling in. Also, I like other side paper, but I mean, because of our paper. I mean, you know, so in some sense, I think something with the field gas inflow.
Right. Right. I totally agree with that. I totally agree with that, except the gas is dissipative. Right? The gas goes in there and changes the gravity. That we know for sure. Right? Another thing we know for sure. At recombination structures were dark matter dominated. At Redshift 3, there is now a rich literature of measures of the dark matter fraction that shows that some galaxies, some massive galaxies, are baryon dominated. The thing is reverted. The gravitational energy has changed. That's it. That's all I'm saying.
thank you very much. Mauro?